Welcome to the last part of this lesson on scheduling, where we will learn about critical path method. So in the last two videos of the lesson, we learned about what is project scheduling and the process to develop a schedule. And we'll learn about how to use WBS to develop the list of activities, estimate the duration of each, develop the logic and the sequencing between them, and represent the network of the schedule and the network of these activities together, considering the relationships between them. So the last step, and actually the pinnacle of that scheduling effort that we'll have a lot of insights from, is critical path method. So we'll learn how to perform the calculations and be able to calculate the times, early and late times, the float, and also at the end kind of really have an analysis here of the criticality of the schedule, which activities should I pay attention to and which ones I can put on the back burner for now. So what is the critical path method? It's one of the very fundamental, very famous methods to do scheduling. There are other methods that are or can be applied in special cases of projects, like linear scheduling for repetitive projects. But CPM is really the heart of scheduling and project management and project scheduling. And a lot of software out there, like Primavera and Microsoft Project, they are based on basically CPM. So let's explain CPM using this small example. Again, we have simplified version of a project here: schedule activities A, B, C, D, predecessors or immediately preceding activities, IPAs, and the duration of each. So it's just very simple project. And if I draw the bar chart here, which actually while I was drawing the bar chart in the second video of this lesson, I was mentally doing CPM calculations. So if I start with the starting activity, which is A, so I draw A from 0 to 5 days duration. B and C depend on A, and then D depends on both B and C, and this means that I have to wait until both of them finish. So I start from 10 and end by 15. So this means the project duration here is 15 days. Now, what do you see special about activities A, B, and D? So they're special because they are critical. Because any delay in A or B or D will result in right away pushing the project finish time further. So if A is delayed 1 day, immediately my project finish time will be 16. So they are critical activities, and usually in schedules they color them by red just to show them how critical they are, and we'll cover more or discuss more how to actually know them by calculations. The next thing here to look at is, now what about C? If A, B, and D are critical activities, now C, what is C then? Of course, non-critical. That's kind of the other binary option we have. But if you look here, if I push C 1 day, the outcome didn't change. I will be able still to deliver this project in 15 days. If I push it another day, say 2 days late now, nothing changed. If I push it or delay it for 3 days now, nothing changed. But it will become a big problem if I delay C beyond 3 days. So that's it. I cannot delay it more than that because it will itself become critical activity and will push my schedule finish time later. So this is the earliest time that I can start C, and earliest here because technically I cannot start before that because it depends on A, and A finishes at the end of the 5th day. And then the latest time is 8 to finish it is the end of day 10. And why it's latest? Because any day after that will result in delaying the whole project and not being able to commit and satisfy the commitment to the project owner and client. So Do I have to do that process in every project? Now I have a project of 4 activities. I can visually and kind of visualize the critical activities and start, moving activities back and forth and see which one is critical or not. But it's not feasible for a schedule that has 10, 20, even, or typical schedules have more than 50 activities, and some schedule have hundreds and even thousands. Not thousands, maybe 1,000 and more, but really typical activity will have like 70, 100, or maybe more than 100 activity. So you cannot do that for every like that visual analysis of schedule to figure out which one is critical and which one is not a critical activity. So we'll do here CPM calculations. So CPM calculations will have forward pass calculations. So you start from the beginning, you set your start of the project at time 0, and you do a forward pass calculations to find what are the earliest times you can start and finish your activities. And then you do figure out by now the finish date and time of the project, so you know the total duration of the project. And then you do a backward pass to figure out what are the latest times start and finish of all activities. And you should end up at the end with also 0 at the end of the backward pass as your start time of the project. We will use activity on node to do the CPM calculations. And this is kind of the template that we'll use to arrange our numbers, because now we have early times and late times, and every one of these will have start and finish. And then I have also the float that we'll discuss the meaning of it. So 5 values are calculated for every activity here. So like for example, excavation is given to us as 4 days activity. So by doing CPM, this activity and the schedule, I know it will start at the end of day 10, will finish at the end of day 14. This is the earliest I can do. And then the latest I can afford will be 15 start and then 19 finish. And then the total float of 5 days. This is kind of an example of how numbers are read on an activity or node activity or representation. So forward pass calculations for the initial activity or activities, early start will be equal to the start of the project, which is 0. And then any following activity, the early start of that activity will be dependent on the early finish of the preceding activities or predecessors. And I will pick the maximum of these. So let's say an activity here, C, is dependent on A and B, and A finishes 7 and B finishes 9, the earliest finish times for them. Then the start time for C, the earliest will be the maximum of 7 and 9, which is actually what we used to do when we were drawing the bar chart. Like we didn't explicitly say that equation or formula, but this is what we're doing. And then within the activity, I'll just apply the duration relation here to figure out the early finish of the activity as the early start plus the duration. All right, so this is moving forward and just focusing or zooming in one activity and figuring out how to do the early start and early finish calculations for it. Now, let's say you did all of that, this calculation for all activities. You reach the end of the project. You have the project duration. Now you do the backward pass. So in the last activity or the finishing activities you have, you will assign the late finish to be your project duration. And then for any other activity, you go backwards. So you figure first your late finish. You figure first the finishing time when you go backward. So the finishing time, the late one, for an activity will equal to the minimum. So now it's the other way. Forward pass we use to pick the maximum of the early finish of predecessors to be the early start. But now for the late finish, I'm picking the minimum of the late start of the succeeding activity or the successors. So for example, if A here is the one I'm trying to figure out the late or apply the backward pass calculations, I will see here that B and C are successors, and I figure out that their late start is 13 and 17. So the latest I can afford to finish A will be the minimum of 13 and 17. Maybe it's confusing for you, but think about it. The latest I can afford to start B is 13, and the latest I can afford to start C is 17. So A, when should it be the latest time to finish it? It's 13, because if I make it 14, or I finish at 14, B is already delayed now beyond its latest time by 1 day. So I pick the minimum of latest finish of latest start of my successor activities and make it the latest finish of that activity. And then do the duration relationship to figure out the late start of the activity. So let's see this example here to show the calculations of CPM analysis. So we have here this project. It has 7 activities. It's a simple project just for illustration. We're given the immediately preceding activities for each one of these activities we have and the duration. One thing to pay attention to is this asterisk that tells us that there is a relation between C and A, and there is a lag in this relationship of 1 day. So if I finish A, I will have to wait 1 day to start C. And what I need here to do the CPM calculations to figure out the start and finish times, early and late, for each one of these, so I can also at the end figure out the project duration. So I start from with the activity on node diagram of the problem, and then I start with time 0 at the beginning of the project. So I start my forward pass calculations. So this means that A and B are starting activities, so they begin the work in their scope at day 0, end of day 0, beginning of day 1. Add up the durations, you will find the finish times, early finish, and then figure out the early start of C, which will be 5 plus 1 or 3. So I'll pick the max, so that will be 6, add the duration, the early finish of C will be 10. This means that the early start of D and E will also be 10. Add up the durations, 12 and 14, early finish for D and E. If you look at F, it will be the same. The early start will be the early finish of D. And then G will have 12 or 14 to be the early start. So I will pick the max to be 14 plus 5 to be 19. And at the end of the project here, I will have 19, maximum of 15 and 19 here. So this means that the project duration will be 19 time units here, days or weeks. Done with the forward pass, I have the project duration, I have the early times of all the activities. Now I need to figure out the late times of activities. So going back, 19 19s, deduct the durations, and then I will have here E. I have only one number coming from one successor G, so that will be 14 minus 4 will be 10, late start. I have here 16 and 14 coming from the successors of D, which means that the late finish of D will be the minimum, 14. So 14 minus 2, 12. I have 12 and 10. Pick the minimum will be 10. 10 minus 4, 6. Then I have here for A, 6 is the late start of C, but I have a 1 day lag here. So this means that it will be the late finish of A will be 5. C, there is no lag, so I just move the 6 here to be the late finish of B and deal with the durations to figure out the late starts. So just to elaborate more on the idea of picking up the minimum value when I go backward. So if we look at D, F, and G, so the late start of F is 16, the late start of G is 14. So the latest to finish D and not cause any delays in F beyond their latest will be the minimum. Because if let's say I picked here 16 to be my late finish of D, this means that G will start 16, which now it's 2 days beyond its latest, and the project will be delayed 2 days. So when you go backward, you pick the minimum of the values you pick from the late starts of the successors. You pick the minimum to be the late finish of the activity you are currently analyzing. So now, once we know the early and late times of activities and project duration, the next thing will be really understanding what's the criticality of different parts of the project. So if early times and late times are equal, this means that I don't have flexibility. The earliest is my latest, so there's no like wiggle time here I have. So this is a critical activity. Any other case like other than that is non-critical activity. So always, of course, you expect your early times to be less than your late times. It doesn't happen that the earliest time you can start is after the latest time. It doesn't work logically. So if this is the case, the general case is early time is less than the late time, not equal, then you have a non-critical activity. The critical activities now, when you figure out, oh, I have these critical activities, I have to look at them and make sure that they are forming a single critical path together. So there's a bunch of them forming a path that's continuous from the beginning to the end of the project, and no interruptions, like there's no activity in the middle is not critical, but the others before it and after are critical. It means there's something wrong. So the critical path is the longest path in the network of that schedule. So that concept is applied in also like transportation engineering and traffic. So if you have a destination and origin and you want to go, you are looking for the shortest path. So in traffic, they're looking for, if I'm driving, I will look for the shortest path. But in scheduling, I'm looking for the longest path because this is the one that's governing the project duration. So a project is a network. You can follow different paths in this network. Every path of these add up the durations. The longest one will be the critical path. I don't have to do that enumeration of paths. Critical path method is kind of doing that scanning and figuring out the longest path automatically. So this is why it's called critical path method, because it's defining the project duration by the longest path of that schedule network. One thing to pay attention to is you might actually have more than one critical path. So by luck or by design, you will have sequence of activities on one path and another chain or sequence of activities on another path. So two paths, they have the same durations, the same longest duration. So they are both critical in this case. So any delay in one of them will cause delay for the whole project. You can actually make all your project paths, meaning that all your activities critical, so you will be on your toe the whole time during the project. So that's, of course, you will be on your toe always, but just imagine being on your toe, managing multiple parallel paths, and they are all critical. It's just crazy. So, but that will help you sometimes in crashing the project duration and making it shorter. And when you make things shorter, this means you do things in parallel, and everything in your project becomes critical. So now, like, if my early and late times are not the same, this means that I can just lay back and have fun. You have to quantify how long you can accept delays in activities. So this is what comes here, what we call activity floats. So float is a flexibility to accept delays in an activity. So every activity will have a float value. And there are actually different types of floats: total float, free float, there's independent float. So the most common ones used in construction are total float and free float. And this lesson here will only covering total float. So total float is the amount of time that I can accept to delay an activity or to accept it being delayed beyond its early start without causing a delay in the project. So it's simple formula here. It's the difference between any early, like the early and late times. Either you're focusing on the start side of the activity or the finish side of the activity. So the example we covered before, for activity C, it will have total float of 3 days, and this is because it's either the difference between the late start and early start of 8 and 5, or the difference between the late finish and the early finish of 10 and 7. One thing to also note here, a disclaimer, is that this formula here is only valid when you're dealing with a simple schedule with simple type of relationship, which is finish to start. Once you do things in parallel and use start to start, finish to finish, this formula doesn't hold grounds, and you will not have it like calculate total float from either the start side or the finish side of activity, and they will be equal. That will not be the case. So we're dealing here with a simple case of schedule that's mainly dependent and represented by finish to start relationships. So let's revisit this example here. And we would like to see what are the critical paths we have and what are the criticality levels and other non-critical activity, or the total floats here. So we see here that we have a single critical path, A, C, E, G, and you see here by noticing early and late times are equal, so all the total floats on that path are 0, and they're causing the project to be finishing at 19 days because the length of that path is 19 days. If I try a different path, let's say B, C, D, F, if I add the durations 3, 4, 7, 9, 12, so the duration of that path is 12, it's less than 19, so it's not the one governing the duration of the project. So that's the critical path. Now, anything else other than the critical activities forming that critical path should have a float. How to calculate it, difference between these two numbers on the start side or the difference between these two numbers on the finish side for this activity and other non-critical activities. So B will have 3 days float, D will have 2, and F will have 4. Well, one thing to pay attention to is that kind of a interesting observation is that this activity F has a total float of 4. 2 of the 4 days of flexibility that I have for F is shared with D. So this means that kind of F doesn't really have 4 days float. It's dependent on the performance of D before it. So if F here, if let's say D here, the earliest to start is 10, but I can start it, like let's say the sub dealing with activity D just decided that, you know what, I don't have the equipment needed, so I will start in day 11. So if this activity starts 11, it's not yet hitting its late time of 12. Its total float now available becomes not 2, it becomes 1. So if it starts 11, 11 plus 2, 13, so this activity will start 13, not 12, so it's also impacted. So if it starts 13 and the late start for it is 16, now its total float becomes 3. So this is why there are a lot of fights in handling schedules between subs, because the sub one that's coming first with a lot of float in their plate, they think it's all mine. Like I have 2 days, I will just have the fun during 2 days and just deliver at the latest time needed from me. You're actually eating up from the float that's given to the following sub. So this is something just to pay attention to, the dynamics of the total floats shared between activities. One thing, some activities will be kind of confined, so the total float available to them is only for them, like B here. So these 3 days total float for B is not shared with the rest of non-critical activities because it's confined by that critical activity C. So that's it for this lesson. We learned about critical path method, how to do it and how to apply it in schedules to calculate early times, late times, floats, how we can also analyze the criticality of the schedules through the floats, and also really understand the dynamics of the schedule, what delays will cause eating up floats and subsequent activities. So it's very interesting management task to do to develop schedules and also control and update these schedules. So thanks for watching and take care.